take the harmonic oscillator, okay? They have something like this. Okay?
Yes.
What is happening? These are the eigenenergies. Okay?
Yes.
This is just like the deltas. Okay?
Yeah.
They're just like the deltas, say, from that time. Okay?
Mm-hmm.
And there is a lower energy state.
Yes.
Namely, okay, like E0.
Yes.
From this, I can just try to be careful with the words.
I can
Okay.
generate.
Okay, I can generate
Yes.
every other
Yes.
state by applying the raising operator.
But because that's one of my confusions. Now, if I take the analogy, I would say that the primary field is like, or the would be the vacuum, would correspond like to the vacuum state. So, whereas somehow here you wrote it's like the delta state. Like, so should I think of the deltas as ends, like the end states, like should I? The eigenstates.
Yeah, the vacuum is just zero. Okay, it has the eigenvalue 0, and the eigenstate, that is the non-trivial eigenstates, if you want. Okay, you should have a gap in the spectrum of scaling dimensions. Okay, say your lowest scaling dimension is this delta.
But
okay, you could have the point is okay. Just it would be like it would be more like a combination of independent harmonic oscillators. Say if you like 1 and 2. Okay. The point is. It's like you're having a bunch of harmonic oscillators, okay?
But just I'm confused about like what is descendant, what is descendant, what is primary, because somehow I thought
the definition is okay. Primary is annihilated by the annihilation operator, which
yes.
is just K.
But which would in this harmonic oscillator mean I have like eigenstates which are the number states n, and only the n equals to 0 would be the vacuum, which is annihilated by, and the others are not. But if I take this analogy, it seems like these deltas are not the vacuum, but are eigenstates n. So it's like one thing that confuses me. And this, if I just take this equation, d delta being I delta, delta looks like the d is a Hamiltonian, and delta is just whatever the z state with fixed number n. So that wouldn't be a primary.
I don't know if you're confusing the lowest. Have to be careful.
Yeah.
Let me just redraw this.
Does this
okay,
make sense to you, or I might just?
I don't know if I'm getting what you're saying. Okay, but okay. Say I found a primary. Okay. With scaling dimension delta. Okay. Associated to this primary, I'll have a bunch of other states here.
Yes.
Okay, by applying.
Yes.
By applying V. Okay.
Yes.
And this looks like an harmonic oscillator, and maybe
yes.
for a specific CFT, this could be the end of the story. Okay, but in general, I can have another primary with another eigenvalue, and then associated with it, I would have another family.
Take it, turn it off, or I don't know. Can I just? Sorry. Okay. Just because, like, here's my point where I get confused. Is like, I would say this is like all the eigenstates n equals 0, 1, 2, 3, and whatever. And they are like, I can see the creation operator I get from here to here, and my vacuum would be 0. Now I always understood.
So the vacuum would be somewhere even lower.
Yeah,
it would be something with 0. Okay, so maybe the vacuum is not 0.
So I would just
have a gap.
Yeah, I would say like you have a 0, you have a 1, you have a 2, and so on up to whatever you want n, and you have like the creation operator generates this, and this would be my vacuum, and this is created. Now I always thought that my primary field would be this one here because it's destroyed. It's destroyed by all.
Okay.
It's destroyed by all.
Of course, the vacuum will also be annihilated by.
Yeah.
If the vacuum has a symmetry.
Yes, but just for example, this one is not destroyed by an annihilation operator. It goes from 1 to 0. This one is not destroyed by an annihilation operator. It goes from 2 to 1.
No, okay.
So these are not annihilated by.
you have the vacuum somewhere here. Okay, this is the vacuum. To get from here to here, you have to apply that operator. Okay. For this, you have to apply this operator, and so on for any other parameter you have. Okay. These guys will be annihilated by Mu. This guy will be annihilated by Mu. Okay. The point, what this is, the vacuum will be annihilated by any symmetry generator.
Does any eigenstate of D is a primary?
So all the primaries and descendants. Well, what is the
the eigenstates.
All these are eigenstates.
Eigenstates
Primaries
of
and
D.
descendants. Okay,
The
these are the conformal. These are the conformal families.
Sorry, I think I had to say correct. So these are the eigenstates of the
D, yeah,
of the
scaling.
yeah. So what are they now? They are primaries. They are linear combination of primaries and descendants. What?
No. The eigenstates of D will be either primaries or descendants.
All these descendant states from delta 1, they are also eigenstates of D.
Yeah.
No, but are they primaries or because
no, they're descendants because they are.
But here you say they're primaries, so no. What?
So I think the primaries, they are the eigenstates, the lowest eigenstates.
That's what I thought. It's like the vacuum, but then
No, there are a bunch of vacuums,
Okay,
right?
it is what you're thinking, but you have to remove the vacuum from the picture.
It's like you pick an eigenstate, of D, then you apply the lowering operator, and you stop suddenly. So that's a primary.
That's
so
a primary.
I get another, pick another eigenstate, lowered, I get another primary. So the primaries are just the lowest.
But then it's a picture of a harmonic oscillator like the vacuum.
What it means to annihilate this guy? If you apply Mu here, you get from here to the vacuum. 0. Okay.
So annihilate the set. The primaries are the set, but
here's the point: you do not get from the vacuum to here by applying the Mu. You get from the vacuum to here by applying some other operator that has that specific scaling dimension. And once you did this, then okay, think about ordinary quantum field theory. You have the vacuum. You do not create states in ordinary quantum field theory by translating the vacuum. You apply you create by applying curation operators. Okay? Does it make sense?
Yeah, I think
I think the picture is like a bunch of harmonic oscillators.
Yeah, it's a bunch of harmonic oscillators.
And
each harmonic oscillator has a different, has its different ground state,
yes.
which is a primary.
Yes.
But the ground state of the whole theory would be the vacuum.
But for example, this here is then not generally true. No, this is not generally primary. There's specific.
Okay. If this will be a primary because I'm using an operator that I inserted at the origin.
Ah, this is one specific. Okay.
Maybe that's why you're missing.
Yeah.
And if I do this,
okay.
for operator outside the origin, I'll get this linear combination, which will be at the center.
Okay. That's okay. That's.
For that guy, will be
Okay,
because
for that guy it's true, but in general it's not true. Okay.
In general,
so that was one. Okay. Okay.
Right. What is that?
No,
At the end, it's just
okay. I was starting like when the questions came, I started mixing up things. But okay, this is fine. And then now for this state, then my Then can I ask another question? Like, because before I made a statement which probably is also wrong, which was that I said all these span the entire Hilbert space, all these deltas. That's what you said at some point.
Yeah, the eigenstates, all the eigenstates of the scaling operator span the Hilbert space. Okay, but
now
do
I reach with them all of them? Do I do all these?
No, all these not.
All these not.
All eigenstates, okay. All eigenstates of D span the Hilbert space. you have two types. You have those that are primaries and you have those that are descendants. Okay?
Yeah,
These
and
two
these
together.
are the primaries. Okay.
So the Hilbert space of CFT is primaries plus descendants. Okay?
Yeah.
They are all eigenstates of D.
And this operator O delta in the origin. So this delta cannot be any one.
That's exactly what I mixed. Like I thought, like it looks like in this notation, given any delta, I just take any local operator with a scaling dimension, and this generates my whatever I want to. So this would mean that all these would span the entire Hilbert space spanned by the states, but this is not true because these also contain descendants.
Yeah, for example, take that your example there, delta plus 1 that you wrote there.
Yeah.
So you cannot, O delta plus 1 is not a primary.
But why then? I mean, I just take
Yeah,
I just take a local operator. I don't get it.
Yeah.
No, but because then then you would have to have something like this. Okay?
Yeah. So
Yeah, this guy would be something like
yes.
this.
So now you. Okay, now.
Then you would apply this to the origin.
But
To the back there.
So that proves that you
You apply
cannot
this
use any delta.
operator. This operator of the origin has this scaling dimension.
but this
But
implies.
it won't generate.
But this implies that this here only holds for the smallest delta that you have. Because I can define any operator as I want with this dimension delta plus 1 or not, and then just say, so this delta
But
has something.
here's the point. You might have some delta 1 and some delta 2, and you don't have, you can't get from one to the other.
No,
By applying this
okay,
operation.
but,
Okay, so
but this, no,
this is what you can have.
but I'm talking about this here. I'm talking
Okay.
about this here. So this delta here has to be like the smallest one.
That delta would be this delta. Would be the prime, the lowest.
The
the smallest.
Okay.
And then
So
every other like this would be just
like
the
this,
same.
I didn't get, like this delta cannot be any scaling dimension, but it's the smallest you have.
Yeah. To generate the
Okay, this was something I didn't get because then it's obvious that I cannot spend by this way my entire Hilbert space. But this is like important, you know, this delta is the smallest that I have. Okay, then I understand. Then this is only subsets of the primaries, the
Yes,
descendants are missing. Okay. Okay, so this was.
maybe I wasn't clear enough when I
No,
maybe I said a bunch of things in written
No,
short sentences.
I mean, for me, I'm sorry if but for me it's perfect because only this way I.
No, it all makes sense.
It makes sense. But
Does it make sense to everyone else?
No, I mean if I'm not okay, but okay, so then I understand this, and then now I understand the statement that you're saying. Well, there's descendants which I can reach by going out of the origin, which I before didn't understand because I didn't get it that this was not the entire Hilbert space. And now the way back, guys. So what is the way back?
Okay, so any more questions about this? Any more questions about operator going to the same?
Okay.
So maybe that picture that you draw there, maybe should have come.
Yeah, maybe. I don't know.
No, there's a suggestion for the lecture notes. Maybe this picture.
Okay, I'll try in the next lecture, in the review of the next lecture, I'll try to draw cube things. Just reinforce the concepts. Okay, so I'm afraid of this bit. Because this is the more abstract one. I mean, so we proved, we have the physicists prove that from operators I can generate all states. Okay, I can generate all primaries from local operators. I can generate all primary states and all descendant states, and these together is make up the Hilbert space.
I still didn't see like all states. I can see that you can get any primary you want, but you can generate some descendants, but I don't see that you generate all descendants. But
Okay, that is included in the physicist proof.
okay. Okay, I can read some of those.
Proof by hand wave.
Yeah.
Okay, okay, bye. That's fine.
I mean, I can look at I don't have it here. I can send to everyone an email with the reference, but I guess the first work that classify all the irreducible representations of the conformal groups by Mack and Salon. So it's a paper that it's titled something like this, like all irreducible representation of the conformal group or something like that. Okay, certainly that paper is really much more mathematical. Okay, and certainly if you read this paper, then you can get the more rigorous proof. Okay, I can just because I don't remember but the names are Mac or something like all unitary representations, something like that. And there's another one by Mac. I don't remember the titles. Mac and Sama. Okay. And there they just do they do group theory, they do representation theory. Okay. This what I'm doing is just more hand wavy, but I guess it is more physical. Okay. So it's like okay, if you accept a bit of hand waving, you can get a better physical picture. And if you want to see the rigorous proof, the more abstract rigorous proof that gives you zero intuition, more or less, then you can go to those words. Okay. I'm not saying this is important because then because of those people we know that we can hand wave here. Okay. But it will be probably beyond my capabilities of reproducing that thing here. Okay. So okay. Let's do the other way. Okay. Local operator. States. Local operators. Okay. Then again, we have to, given a state, find an operator. Okay. How do we determine an operator? Again, we can define an operator to be determined once we know all of its correlation factors. Okay, because it encode all the physical information we can get from a given theory. Okay, so let's look if I have a state delta. Okay, and work with primaries. Okay, so I know that this primary state delta can be generated by that, by this definition, by an operator with the same scaling dimension inserted at the origin. Okay?
But this is a very specific state, that's not a generic state.
Yeah, we get that. Okay. And then I do this again for every correlation function, meaning any combination of fields here, whatever, every field that has one theory. And then I say, okay, I determine this state. Okay? Then I do this for every other primaries that I have, so I determine the states for the operators for the primaries. Okay? If I have a descendant, okay, so I would instead have something like this. I would have okay. I would have something like this. Okay. And then hand wave there is inserted the same hand waving that happened there. And then this guy, I'll do the same thing here, and then this acting on the back end will just drop, and then I'll end up with something like this. Okay, and this guy already know. Okay, this guy is another operator. Okay, this is another thing of conformal field theory. When we say that's why we use operators and fields interchangeably in CFTs. Okay? When you say operator, it can mean anything, okay? Including like exponential, arrays, exponential operators. You can, like, if you, I don't know, if I'm crazy enough, I can go like with some cosine of the field finder. Okay? Anything that looks like an operator is not allowed operator to be inserted in a correlation function. Okay? If it is a primary, then I can apply those. If it is a primary, if it ends up being a primary operator, I can apply what you know about the correlation functions of the primaries, okay? So, might be read to first glance if you use only to usual quantum field theory to look at the correlation functions of an exponential and the other fields, but in CFTs it really just doesn't matter, okay? It's just an operator just uses any other, okay? And okay, is it everyone satisfied with this proof? I mean,
no,
yeah.
at least I understood now what it's about. Yeah. Okay, no, it's fine. Yeah.
Again, another point is that this proof is just like a priori proof. Okay, we can do this in principle. Okay, I'm not doing it. I won't I won't select a CFT, and I won't do like this thing. That okay, let's find all the permanent states by playing this game. Okay, the real value of this discussion is to we only need to know that we can do this in principle. Okay. This allows us to prove that it allows that we have an operator state correspondence. Just it doesn't mean that we can just use it just like a 1 plus 1 or something like that. Okay. And the usefulness of taking all this time to discuss operator state correspondence, which is then just local operators. One correspondence with the Abel space states is that this will improve the operator product expansion. Okay? The operator product expansion in usual quantum field theory it is an asymptotic expansion. Okay? It only works if the what is that? Okay. This is just this won't be the whole concept of the operator product expansion that I will cover in this lecture. Okay? Just I mean what it is about. Okay? I have two operators here. You know, any quantum field theory, okay? I have two operators. Okay? It is a statement that to this I can, and if you really want to be really rigorous about this, this is one axiom, okay, of quantum field theory, non-perturbative quantum field theory, and it is a number problem whether this can be derived in some other way, and it's correct, and we can use this to substitute perturbation theory, something like that, okay? But if you go too deep, then you find that it's kind of an axiom, and it is known to work pretty well in some situations, okay? One situation, okay? So I said, the OPE is an expansion. I take two operators, okay, a point X and a point Y, and substitute them by a series of operators of the same type. It could be operator 1, operator 2. Then I can have A operators here, located in a point, say, in between them. For example, okay, with some, of course, there's some coefficients here that depend on the operators that I have on the side and on the operators that I have on this side. Okay, this is an expansion. And in a standard quantum field theory, this can be a good expansion if these guys are really close, okay, to each other. Okay, so it is like an ultraviolet expansion. It works in the ultraviolet. Okay, because they are really close to each other. If you take any one of these operators far away from the other, then this expansion will break down. This is really used in quantum chromodynamics and I forgot. One example that is used all the time is quantum chromodynamics. Okay, but most of its uses reside in CFT. Why? Because this picture, this convergence of the OPE gets enhanced precisely because of this. This is what we're discussing on the next lecture. This correspondence will will improve this convergence. Okay, it will converge. If I take any other two operators, this expansion will converge for any distance as long as I do not cross another operator. Okay. So, to use this picture, here, if I have an operator here, this will converge in any radius, okay? If I only have these two operators, it will converge on the entirety of space. If I have another operator here, this will converge until it hits this operator, okay? But it's much better than only converging like for really close points, really space points, okay? And
so for
this will be
point correlated function, it holds for all distances.
What?
for 2-point correlation function, it holds for all
Okay, for any two operators. So if I have a 2-point function, I can play this game. If I have an n-point function, I can play this game for any two operators and do it iteratively. And this is actually how we relate rather anticipated content on the operator part expansion. This is how we relate n-point function to n minus 1-point function all the way back to 2-point function that we know exactly by conformal symmetry. So that is how we will be able to compute the structure constants and the conformal blocks. Okay, it is because the convergence is improved by the operator state correspondence. Then we can do this and just in the end transform, map this problem to a problem in linear algebra and tell the computer to solve it. Okay, that is what it was done in those. They're still here. When people study the Eisen model, what's criticality in 3 dimensions. Found all those scaling dimensions and all that. Okay, so it was basically that. So that's why we learn about next lecture, and then also discuss this next lecture. Okay, Unitarity balance, and that's it because the people that are going to have class.